Before we can look at inverse matrices, we need to review the identity property. The identity property of addition looks like this. If I start with a number and I add something to that number and I get that original number back, that's the identity property. In the addition world, I need to add 0. 0 is known as the additive identity. The additive or identity property of multiplication works the same way. I'm going to start with A, and I'm going to get A for an answer, but instead of adding something, I'm going to multiply something. So A times something gives me 1, or gives me A for an answer. In the multiplication world, I need to multiply by 1. So 1 is the multiplicative identity. We need to know the identity in order to do the inverse property. The inverse property works this way. I'm going to start with A, I'm going to add something, and for an answer, I want to get the additive identity 0. In addition, I'm going to have to add negative A, the opposite of A, in order to get 0. The additive inverse is the opposite. Think of this as opposite, not negative. That way, if A starts out as negative, the opposite of a negative is positive. The inverse property of multiplication. Again, I'm going to start with A. I'm going to multiply by something, and I want to get the multiplicative identity 1 for an answer. So A times something equals 1. A times 1 over A gives me 1 for an answer. 1 over A is the multiplicative inverse. One over A is the reciprocal of A. The identity property of matrices. I'm going to worry mainly about the multiplication version of this property. In the matrix world, the addition property isn't too different, but the multiplication is going to be different. In the matrix world, I'm going to start with matrix A, and I'm going to multiply by something, and I need to get A for an answer. So what is that something? I need to multiply by the identity matrix. So what does the identity matrix look like? Well, the identity matrix is going to be a square matrix. And if it's a 2 by 2 matrix, I'm going to have 1s across this diagonal and 0s across this diagonal. If I have a 3 by 3 matrix, I'm going to have 1s across the major diagonal and 0s every place else. I can keep going to make any sized matrix, as long as I have 1s across the diagonal and 0s every place else. So the identity matrix is a matrix where the major diagonals is filled with 1s and I have 0s every place else. The inverse property of matrices. Again, I'm going to only really worry about the multiplication version of this. The additive version isn't too different than the additive version in integers. The inverse property of matrices looks like this. I'm going to start with matrix A. I'm going to multiply by something, and I need to get the identity for an answer. So what do I need to multiply by? Well, I need to multiply by the inverse of matrix A. This little -1 power means inverse. Now, in order to find the inverse of a matrix, there's a formula. The formula for the inverse of a matrix, if we have a 2 by 2 matrix, and I'm just going to let that matrix be A, B, C, D, where A, B, C, D are just numbers, then the inverse of that matrix is going to equal 1 over the determinant of matrix A times a matrix where I'm going to switch the numbers around. I'm going to take my value in the lower right corner and put it in the upper left corner, and I'm going to take the value in the upper left and put it in the lower right. And then I'm going to keep these two numbers in the same spot, but I want the opposite of those two numbers. So in order to find the inverse of a 2 by 2 matrix, I'm really combining the reciprocal, but I'm going to use the reciprocal of the determinant, and the opposite. I want the opposite of these two numbers with these two numbers switched around. Let's try an example. Let's say I want to find the inverse of 6283. The notation for inverse is raised to the -1st power equals 1 over the determinant of my original matrix, the reciprocal of the determinant, times this matrix all mixed up. I'm going to switch these two numbers around, 3 and 6. I'm going to keep the 2 and the 8 in the same spot, but I want the opposite of those two numbers. These two numbers are both positive, so I'm going to make them both negative. If they were negative, I'd make them positive. Now I need to do this math. I'm going to start with the determinant. The determinant of this 2 by 2 matrix is going to be 6 times 3 minus 8 times 2. I'm going to keep going with this math. 18 minus 16 is 2. So now I have 1/2 times this matrix. In order to do scalar multiplication, I just need to multiply this number times everything in my matrix. I need to distribute by 1/2. 1/2 times 3 is 3 halves. 1/2 times -2 is going to be -1. 1/2 times -8 is -4. And 1/2 times 6 is 3. So the inverse of 6, 2, 8, 3 is 3 halves, -1, -4, 6.